Vasilis, you are a senior CNRS researcher at the Institute of Ecology and Evolution at the University of Montpellier in France. And you are interested in ecological stability, tipping points, and the effects of eco-evolutionary feedbacks on ecosystem resilience under global change. And today you are presenting expecting the unexpected early warning signals for tipping points. Thank you so much for being here with us today.
Thank you. I hope you hear me
perfectly.
Well, good morning, everyone. And thank you very much for the invitation. And thanks for organizing this meeting, Emilis, taking care of us. As you may, thank you for the nice introduction. Yes, I work at the University of Montpellier in the south of France, on an Institute of Ecology and Evolution. So I have a little bit of a perhaps different background compared to what we heard yesterday. So next slide. So I would like to start with acknowledging, and I guess most of us agree in this room, the fact that we are living in times of high uncertainty. And that is because we are facing, next slide, huge ecological and environmental challenges. Basically, we have to deal with the loss of biodiversity, with the emergence of new diseases and pathogens, with the degradation of very important ecosystems at big scales, like the Amazon forest, and even with the possibility of abrupt climatic shifts. And slide before, thank you. So as you see, all of these very diverse examples and challenges have two things in common. First, they're associated with the possibility of a tipping point. And second, being associated with the possibility of tipping point, it seems that apparently it makes it easier to get on the front cover of the Guardian. So, joke aside, tipping points perhaps is not just a buzzword. Now, this next slide. Because, for instance, in the history of climate, in the history of Earth's climate, there have been a lot of periods where we have experienced this type of abrupt responses. This is the example of the thermal line circulation, which brings warm water from the Gulf of Mexico up to the coast of North Europe, keeping the climate stable, which more than 12,000 years ago relapsed, the circulation stopped, and as a result, the Earth shifted to a much colder state. Luckily for us, things recovered and we're living in this constant climate during the last millennia. However, there is a chance that the same collapse will happen in the future. Next slide. But also in other systems, we have a lot of examples of population crashes. This is especially in fisheries. This is the example of the Atlantic cod that in the early 90s collapsed due to probably a combination of overfishing and climate change. Next slide. We have iconic ecosystems like the coral reefs that can shift from a healthy reef full of fish to a degraded reef overgrown by microalgae. And next slide. And we have the example of lakes. We know that shallow lakes can shift from a clear water state to turbid water state due to eutrophication. So next slide. So for all this diverse type of ecosystems, basically the question that we are facing, or at least one question that we're facing, is whether we can detect this type of tipping responses in advance. So next slide. So today I would like to introduce you a little bit on the research that we have been doing for the last more or less 10 years on developing early warning signals, EWS, for tipping point detection, to give you a little bit of the basic idea and present with some examples of how we can apply this type of indicators in practice. So next slide. So to do this, we have to go back to basic systems theory. And in basic systems theory, next slide, we can expect that systems can respond in two ways. They can either respond I hope you see my arrow. Yeah, hope you see my arrow. They can either respond, okay, in a gradual way. That means with a small change in the environment will create a small change in the system state, or abruptly. Next slide. So in this case, and this is actually the case of the abrupt change, is the case that we expect and we assume that all these type of systems I presented you before belong to. In this case, a small change in the environmental conditions will lead to no very big change in our state of the system until the point where we're reaching this tipping point, this mathematically catastrophic bifurcation, where we're going to be shifting from the current state to an alternative state. So you're shifting from this line down to this line. Next slide. So the interesting point with this type of transitions is that if we would like to restore the system back to its previous state, we'd need to restore the conditions on a much lower level compared to the level where the tipping point occurred. So from here, we need to restore the changes back to much lower level in order to get our system back to where it used to be before. So before I go on, next slide, I would like to introduce two notions, the notions of define what I mean with tipping point. That would be a situation where you will have an accelerating change that it will drive the system from its current state to a contrasting state. And the idea of ecological resilience would be the magnitude of disturbance the system can tolerate before shifting from its present state to an alternative state. And the reason I'm doing this is because, next slide, these two notions are linked. So whenever I will be talking about the loss of resilience, I would imply that I'm also assuming that there is that the system is closer, there's proximity of the system to a tipping point, and that's a high risk of the system of approaching a tipping point, and vice versa. So next slide. From systems theory, going back to systems theory, we know that before this type of catastrophic bifurcations, before this type of tipping points, we know that systems tend to slow down when they're close to these thresholds. Basically, the dynamics of the system start to become very, very slow. Because of that, next slide, we can take advantage of that slowness and derive at least three ways that we call that can indicate to us that our system is closer to a tipping point, and we call these three ways. These three ways constitute our early warning signals. So first, next slide. What we see is that if the system is closer to a tipping point, it takes more time to recover after a disturbance. Next slide. If we will be monitoring the system, we will see that the system becomes more variable close to tipping point. So variability in the system will increase. And next slide. And if we observe the state of the system, we will see that it starts to look more and more similar to itself. So today, we'll start to look, we'll start to look more like tomorrow. In other words, autocorrelation in the system will rise. So these three indicators actually represent the three ways of measuring our proximity to tipping point. So the first one, already you have, as you see in this next slide, they are a direct type of indicator, meaning that they will require a disturbance experiment. Next slide. For example, here this is an experiment we did in the lab, where in a device, in a chemostat, we were growing phytoplankton. Phytoplankton is a plant, basically, that lives in the water. So we know that these populations of plankton, they need light to grow, but if the light becomes too strong, then they can't sustain any more light and they die. So during this experiment that took around 30 days, we increased light intensity, and we observed that the population indeed at some point collapsed to extinction. But what we were interested in was that during this period of the experiment, we perturbed the system, in these 6 ways by removing some standing biomass. And we found, next slide, that the time or the speed with which the system was reacting to this change was reduced, which actually implies that we could identify slowing down in this living system as we were expecting from theory. Next slide. These 2 other indicators are more indirect indicators because they would require that we'll have long-term monitor data. Next slide. As an example, we go back to the thermal line circulation, where we could try to see if we could identify slowing down by looking in the past. So next slide. We used past paleoclimatic records that are represented with the black line here, that represent the collapse of this type of climate subsystem. We ignored the collapse, what happens after the gray zone, and we only concentrated on what happened before the collapse. And within a window that was half the size of the time series, next slide, we measured autocorrelation. And then we moved this window forward until the collapse. And what we saw was a positive trend in autocorrelation, which implies to us that indeed in this type of very big system, we could identify critical slowing down. Next slide. In fact, all of these were nicely summarized in a review that was done back in 2009. And next slide. And since then, we have a big production of work that is related to try to apply this type of early warning signals in very diverse disciplines, not only in ecology and climate that I mostly talked so far, but also in engineering or even social sciences. So next slide. So I would like to finish up by giving you a couple of examples of how we can use them more generally. So we can use them for monitoring. So we have this long-term data and we want to infer the risk of a system of potentially leading to a collapse or to tipping point. So next slide. This is the example of trying to infer risk of tree mortality in forest paths in California. As a proxy, here it was used NDVI, which is a measure of the greenness of the forest paths. And what we know from this record is that in 2016, that forest paths died. In this below panel, you see the evolution of autocorrelation in the system, where you see that even 2 or 3 years before the collapse, the autocorrelation increased much more compared to the reference autocorrelation that it was measured in this system. And that could be used as a way for inferring that the system is approaching a collapse and is losing resilience. Next slide. We can also use these indicators to rank systems. We can rank different species, different subsystems in space, or different situations. So for example, next slide. This is again an example with remote sensing data using again NDVI, but this time is forest patches in the Amazon basin. And here what the authors have done is to measure autocorrelation in its forest paths. The more green the dot, the higher the autocorrelation. In this way, one can infer that the more green dots belong to actually, here something happened with the PowerPoint because it's too many green points, actually to be the reverse. There are more patches, there are less patches that have a higher autocorrelation, but these patches in any case could be interpreted as patches that will have a higher risk of experiencing a tipping point or are more sensitive to change. Next slide. We can also use the same indicators for mapping across big scales, you know, like, yeah, mapping across the big scales, these early warnings. So this is an example from a climate-produced data. This is future climate temperature. Basically, what we did here was to compare the variability at the end of the 21st century compared to the variability at the beginning of the historical record. And we did it for using climate projected output. And in the next slide, we can see how change in variability will look like in the future. What we see with this picture is that we confirm what we already know, that areas that are more red are the ones who are going to experience higher variability, and they belong more to areas like the Amazon basin, Sub-Saharan Africa, or Southeast Asia, compared to the blue areas that are going to be actually enjoying a less degree of variability in the future, mostly like high latitudes in the North Hemisphere. The next slide. But I can give you a couple of examples that go beyond ecology. For instance, in the next slide, you will see that we can study episodes of depression in patients. So this would be changes in autocorrelation and variance in depressive patients before an incident of depression, where actually they was able to show that autocorrelation and variance of emotions are higher in people who are more close to a depressive episode. And next slide. Okay, something went really wrong with this figure. I'm really sorry. That's the PowerPoint doing its own thing. So basically here, you can't make anything out of this slide the way it looks now. But the point is that we can use here in this study, they used the mumps outbreak as an example, where they showed that based using a risk assessment method based on these early warning signals, it was possible to detect the outbreak of mumps almost 5 years before actually it happened. The next slide. And of course, just want to say that there are limitations to this approach. It works quite well, but there are some things to consider, like that these are generic indicators. That means that is very powerful in their application because we can apply them almost everywhere. However, they're not specific to tipping points, but they then occur before other types of bifurcations. They're not predictive. They're not going to tell you when the tipping point is going to occur, but they're going to tell you the direction, whether you're going to the wrong direction, closer to a tipping point than avoiding a tipping point. And also they have practical difficulties because they're related with data issues, as most of these methods are. However, I gave you some good examples, and most importantly, we have by now a very good theoretical and methodological background to apply these indicators, not only on time series, but also on spatial data, which I didn't have the time to show you today. And also, next slide, we are developing similar approaches using structural and trait-based data. And with this, I would like to thank you for your attention.